5 by Pourier Hosseini, section M07, the motion of falling objects. Now the objective of this lab is to analyze objects in free fall and the effects of gravity and drag on these objects. So for my first object I used a plastic water bottle. This is the object that was supposed to move fast or have very little drag. As you can see, it falls. The delta t for this one was chosen to be 0.01. Well, actually for both videos it was 0.01 because both videos were about a second or so long, and 0.01 would be a good estimate of our motion. The length of the bottle was set to be at 0.22 meters, and the origin was placed at the center of the bottle, and the y-axis, the negative y-axis, would put in the direction of its motion. The same thing was done for the other video. Here you can see the other one. For this one, I had to use the width of my face as the calibration for this video because I threw away the piece of paper before I were spliced so that the initial position and velocity models were made. One was a model of an object falling without experiencing drag, and one was a model of an object falling while experiencing drag. So for both videos, the time step of 0.01 was used, and when creating this simulation, the momentum principle was used to construct an accurate model. Now, using the momentum principle, the velocity and position of each object was updated each tenth of a second, creating an approximation for the motion of the object. So first I will run the object falling without experiencing drag. Now, as you can see, the motion of this object is parabolic, which means it's accelerating throughout its fall. So if we go ahead and run the simulation for an object experiencing drag, we will see that instead of a parabolic motion, it will actually even out and become linear. This is when the velocity remains constant. This happens because the force of drag is equal to the force of gravity after some velocity, and that is called the terminal velocity, when the velocity will remain constant. Now there is a constant of proportionality which has to be calculated. This was calculated by running the program multiple times and seeing which constant of proportionality. See when both the model and the observed data are graphed, they fit together pretty nicely. So our model was a good representation of our observed data. They don't fit together perfectly, and this is because of some human error while using the tracking software, and some forces that weren't accounted for. For example, in the model, the drag force was determined to be 0, while in the observed data, even though the bottle experiences very little drag, it still does experience some drag. This graph over here is the model and the observed data for a free-falling object that does experience drag. In this case, it was the piece of cardboard paper. So as you can see, again, the model and the observed fit pretty well together. The variance again comes from human error, and it also comes from the constant of proportionality, which, if determined more accurately, so for the what does it mean question, here is the velocity versus time graph for an object with no drag and an object with drag for the models that I ran. As you can see, the model the model with drag, actually the velocity evens out at about -1 meters per second, while with the no drag the velocity continues to increase as it falls. Now, it is obvious with the graph that the model that includes drag is the one that clearly shows the terminal velocity. So for the what if question, I've already ran the model including an initial downward velocity with experiencing no drag in free fall, and as you can see, it doesn't change the graph much. It seems like it just starts at a higher velocity and it continues to gain speed as it falls. But if I run the model that includes drag force, as you can see, the entire graph is a straight line. There is no curve, there's no acceleration. That is because the object starts at a velocity, and depending on what that velocity is compared to the drag force and the constant proportionality, it will speed up or slow down until it reaches that initial that terminal velocity, and then it stays there. I happen to pick a velocity which was